Okay. Maybe I'll start off with a little background. I'm going to thank the people that have been involved in this work. Mainly, I want to focus on the Iowa State. I taught at K-State, about flubbed up there, but anyway, the Iowa State University collaborators, Dr. Jianming Yu, Ashish Singh, and Jody Edwards are those who have been working with us for the last 3-4 years. And then corn growers have contributed obviously considerably to the work with Jianming and with Jody. So I taught at Utah State University for 3 years, transferred to the University of Kansas, taught there for 19 years. I was the associate director of the Kansas Applied Remote Sensing Program. And then I taught in the Department of Agronomy at Kansas State University for 5 years, and I saw Bill Shapaw's name come up. I've done collaborative work with Bill as well, and started working in genetics. I'm going to introduce you, I've been used to working with satellite imagery, but in 2013 when I transferred to K-State, they yawned when I talked about satellite imagery because the pixels are too big. They can't see their plants. So I started working with some of our K-State colleagues flying drones and collecting imagery, and it's a whole new world. It's not like traditional remote sensing. Now our pilots, Kurt DeMuth here, you see, he's flying in Florida, flying 1.5 million acres of area to map flooding problems that they've got there. And we just flew Houston. So we don't just do agriculture, but we're doing a lot of ultra high resolution remote sensing. Kirk used to escort the Predator back into the U.S., to give you an idea. I said, Kirk, how do you dare fly these really expensive? I mean, that one right there is $250,000 drone. How do you dare fly those drones? He says, it's scary. I said, what do you mean? He says, and they crash too. And I said, have you crashed one? He says, I probably have crashed $1 million worth of drones in my career. So he wasn't bragging about it, but what it says is you don't get to fly a $250,000 drone unless you know what you're doing. So our guys didn't just cut their teeth on flying a little white Phantom around, and they're some of the best drone pilots in the world. So there's basically two types. There's what we call a multi-rotor, and there's a fixed wing. The multi-rotor, a couple of 100 acres a day if you're doing mapping quality work. Fixed wing, 1,000, maybe 1,500 acres a day. The Cessna, 250,000 acres a day. So we use Cessna from an economic standpoint. We can still get 2-inch resolution. But with these, the multi-rotors, we just flew data here at Iowa State last week. We were doing 2mm pixel sizes, so we're mapping, almost could see the veination in the plant leaves. Here's a quick little video. Daniel is one of our pilots. He manages an airport in Colorado. He's licensed to train you in how to fly twin-engine jet aircraft if you want. Again, these guys are not, they are some of the best. That was some of the work we were doing for Ashish last year. So it's just showing a multi-rotor. They're really, really good for doing research work. You can fly them slow and low and get really good high signal to noise imagery. The little teeny aircraft that you fly have a really bad camera on them. The sensors in those little cameras are smaller than the sensor they put in the pink Barbie doll camera, all right? Just so you get an idea. And they're really got a very low signal to noise ratio. Now, when I was working with Bill, I grabbed some leaves off of soybean at different stages of senescence, and I took a spectral radiometer that measures 2,151 bands, and I took readings off of each of those leaves and then plotted the graph for them. So this is percent reflectance, and this is wavelength. And this is the visible portion. I've got a visible bar down there showing you what colors are associated with the graph. That right there is telling you, do you see the blue band? All the lines are on top of one another. There's no discriminating power there. It's the green band and the red band and the shoulder on the near infrareds where your information is. The rest of it is mostly very similar. When I do covariance analysis or look at collinearity in the data, The R squares between one band and the next is 0.999999. It's just highly intercorrelated. So you talk about a problem with inverting your matrix. This is a big problem when we start trying to do hyperspectral, is that you've got so many bands you can't work with it because they're highly intercorrelated. But if I'm trying to tell, this is the dead leaf, the dead leaves start looking like bare ground, and that's almost like a bare ground spectral response pattern. So use, you only need, in my opinion, you only need a band here, here, and there, and you've got all you need. You don't need hundreds and hundreds of bands to get the job done. Now here are 3 bands, a blue, a green, and a well, the red one's not there, and a near infrared band. I would usually use a red before I'd use a blue band, just for the reasons I just showed you. And this is what we call a color infrared image. Often people say, that's a near infrared image. I say, no, this is a near infrared, this is a color infrared. This is the combination of visible bands and a near infrared band, so we call that a false color composite or a color infrared image. And that one over there is the near infrared band. Okay, here's a soybean plant with, looking at it as if you had glasses on that let you see the blue energy reflected, the green energy reflected, the red energy reflected, and the near infrared reflected. Notice this is the healthy part of the plant. I didn't show you the visible, trying to save time. But that dark part, the reason it's dark is it's absorbing energy. And it's absorbing energy because that's the part that's photosynthetically active and still able to photosynthesize. And so dark means good in visible bands. Red, the plant's using red and blue for photosynthesis. It reflects more green than it does the others. That's why plants are green. And the near infrared, it reflects a lot of near infrared. I don't have time to explain why, but near infrared is highly reflected by anything that has chlorophyll. So we compute an index that Peter talked about earlier. It's called the Normalized Difference Vegetation Index. Here's the formula graphically. Near infrared minus a visible band, usually the red or the blue, or the green. Actually, I prefer the green. Near infrared minus green, I'll say, divided by near infrared plus green equals NDVI, all right? That's what it is. It's a normalizing method that takes advantage of the fact that as you increase biomass or chlorophyll concentrations, you get a higher reflectance in the near infrared and a lower reflectance in the visible. And so the greater the difference, the more biomass or the more chlorophyll. So here's just a colorized NDVI map. There's the healthy part of the plant and the sicker parts of the plant. And we fly this 2 millimeter resolution. We compute an NDVI for every 2 millimeters by 2 millimeters on the ground to give you a real detailed map. This is just a picture I took of a soybean field in color infrared. Give you an idea, you can see the trees. The redder it is, the greener it is. Just think green, red, green, and you'll be all right, all right? All right, so Ashish, let me throw in a couple of slides showing you. These are some of his plots where he's got different genetic varieties put out in single plants. This is the calibration panel. This is those are ground control points. I'll show you later why that's important. If you're doing multi-temporal analysis, you need ground control. All right, this is what it looked like on the ground. He had replicates of four rows. So there's a calibration panel. There's a ground control point. And here is an aerial view. There's an example of 4 of them with a control point in color infrared. And this is what it looks like later on. After the canopy is coalesced, notice the genetic variation you're seeing in that field in coloration. All that variation you're seeing is differences in chlorophyll, canopy leaf area index, biomass, whatever may be there that's causing the canopy or the geometry of the canopy to change. And that one is either early senescence or sudden death. I'm not sure which one took that one out. But all right, at Kansas State, had one of the agronomists go out into one of his fields. These are the earlier planted soybean. These are the seedlings. So it goes from older to younger plants. He went in and defoliated a row, just a strip along there, and then he pulled out some plants along here. There's a calibration panel. This one he did nothing on it, and this one he sprayed it with 2,4-D about 20 hours before we flew it. And here is an NDVI. Oh, by the way, that's me right here. And that's me, and that's me, and that's me. This is an ortho mosaic of about 40 images put together into one big ortho. This is an NDVI map. Notice we picked up the strip where they put the 2,4-D down real quickly. You can pick out where he used the defoliation, kind of like with hail damage, and we're picking that out. The missing plants, obviously you can see where they're missing all over, and you can't see where there's anything done there because there's no treatment. Here's a corn. We were doing nitrogen studies at Kansas State. This is a sandy patch going through color infrared, and we happened to get soybean in the picture, so I thought I'd show you this. Found out later what was going on. I was trying to figure out what is going on with this field. Notice that the soybean up there is still green, has a high NDVI. These are varying in their NDVI, and the reason they're varying is because they're dying from sudden death syndrome. The ones up above were treated. I don't know what the treatment was. I know the company, but but I don't know what the treatment was. But whatever they did, it's certainly making it so those soybean plants are doing all right compared to the others. Now you say, okay, those are pretty pictures. No, it's not pretty pictures, only pretty pictures. We can take samples of those plots, pull out the data, and we have millions of pixels. Many of the plots will pull up over 30, 40,000 pixels in a sample and be able to analyze those. And these are the graphs for each of those three plots. There's the three different graphs for the plots showing that they're different, they have different values, they have different distributions, and so on. When we flew this field, this is corn, flew this one for Jianming Yu. We flew a 2-acre field, 640 images in just 2 acres. It was, they're each 8 to 10 megabytes. It was 5.6 gigs of data for a 4-acre field. And then we have to take all those images and put them together, and those are just some of the products that come out. And these are ortho mosaics. All 600 images, we flew it 3 times, ortho mosaicked, so that you can see all the genetic breeding plots. And what we've done is we've corrected for the viewing angle. If you have the camera here and take a picture this way, or the camera here and take a picture this way, you're going to get different values. So you have to correct. And so we have 15 or 20 overlapping images, and we use all 15 or 20 for every pixel to calculate the bidirectional reflectance distribution function and remove that error in the image. Now, this is to show you the band-to-band or the image-to-image registration. If you're going to extract data from multiple dates, you got to have those images perfectly registered. Notice that X is not moving. If that X moves, I think we've got one more swath. This is natural color. If that X moves, then we haven't got it registered. That's called co-registration, and we work to get those perfectly registered. All right, to finish up, this was some work we did actually in 2014, but I think it's got an interesting story, and I've shown it to here before. I apologize, those who've seen it before. This is biomass studies, genetic biomass work. And this is the imagery. It's so detailed, we're looking at the paper sacks on the corn plants, or sorghum, I should say, it's sorghum, biomass sorghum. We classified the image, removed the shadow component within it. We classified it into lower leaves, middle leaves, and upper leaves on the plants. And then we calculated the geometry of each of the leaves to see which way they were going, whether they were erect or whether they were more decumbent. So here, this is a zoom in on the classification. And here we took a strip, we pulled out all of the classified along that track, pulled them out, and then we pulled the data out from each one and built bar graphs for each of those plots. Plot number 1, what it's showing us is that there's more lower leaf showing in than there is upper leaf. Because the bar here is higher, we've got a more leaf area of the lower leaves than the upper leaves. What does that tell us? It tells us that plant has the upper leaves more erect, and the bottom leaves are more decumbent. If you're breeding for increased biomass, you want more leaf area, and you increase your leaf area by getting your top leaves to get out of the way so sunlight can get deeper into the canopy. So we pull those, we've got all of that pulled out, and just a graph here. So here, plot number 24, notice that it has more lower leaf showing than upper leaves. So in other words, I'm going to select for that phenotype. And the next one, it got more lower leaves than upper. I'm selecting for that phenotype. These two, just the opposite, I'm going to select against them. So I'm trying to decide which phenotype I want. Here we're seeing the seed heads. So if you want to count seed heads, you can do that too, and the size, get the idea of the size. And the last slide, this was some imagery over Jody Edwards Field. I showed this to Jody. Jody works with the ARS. I said, Jody, what do you see in here? He says, I see I'm not going to be using that field anymore. I can see all kinds of problems in it that I didn't realize were there until I saw the imagery. And he said also, these plants, the brown ones, they're already browned down. They're senescent. He said, I'm going to check the yields on those and see, because those are early maturing plants. I'm going to select for those if they've got a high yield and high quality grain. Those are the ones I want to select for. He said he had over 33,000 plots, so this was obviously a time saver. So if you do the data, if you collect this kind of data over time, you can start using the traditional agronomic curves or growth curves to see how the plants are growing. You can plot their way they're greening up. You can determine the percent cover, how the plot is changing from date to date. Right now we've got a grant working with Jan Ming on looking at how different sun angles change, solar zenith angles, change the values that we get so that we know whether or not what's the best time of the day to try to capture the imagery. All right, I think that's it. Any questions? Oh. Did I make it in time? Oh, lots of time. Huh? Yes. No hard ones. Just kidding.
How discriminate? Could you make the color?
How well can you discriminate in the colors?
Yes, within
okay.
the colors.
The human eye can detect 15 intensities of energy. Okay. The camera we're using detects 34,000 different intensities of energy.
But within the same wavelength?
We're using the same wavelength in the camera. We've got the same wavelength. The challenge is all the variability. You know, Peter talked about using the calibration panels to calibrate the data. The problem, that's not a problem. That's a great idea. The challenge, though, is that the differences in sun angle creates different shadow patterns in the canopy. And shadow is the biggest factor influence spectral variability in your plants. So what we have to do is we actually go in and try to mask out shadow if we need to, depending on what we're doing. But yeah, there's lots of variables. Just like anything else we do, there's tons of variation we have to control for. The trick is knowing what it is and knowing that it's there so that you do it. Yeah. Uh-huh.
Can you touch on the software you're using? Are you using AgPixel software, or do you guys use other? We have a software called AgPixel, which allows us to extract values, but we use we spent $2 million wrapping programs around the conventional software that's used for orthomosaicing, which is the Pix4D and AgiSoft. Those are out there. We've also got many years of experience in knowing what to do so that when you fly it, you can still get a good orthomosaic. It's pretty challenging. The life expectancy of a drone is about, in my opinion, is about less than a year if you don't know what you're doing. So if you're going to spend $15,000 on a drone, plan on being crashed and picking up in a black garbage bag in that year, unless you really know what you're doing, all right? I'm throwing some dampers on this because I don't want you to go out and say, oh, let's go buy a drone and then get out there and start flying. Also, you need to have FAA approval. You got to have a 105, or else if you mess up, the university finds out, you'll probably be looking for another job. So